Hey everyone, welcome to NPLAN's Paper Club. This week, Dwane is going to be presenting a really cool paper on a new form of neural network, which is more explainable and has a couple of other key benefits. One of the ones suggested in the paper is like generalization, but I'll hand it over to him.
Okay, great. So I was drawn to this paper basically because of the explainability and then the number of graphs in it that then sort of just hooked me and grabbed me in. And I'd like to probably start from one point that was it Cynthia Rudin made, which was stop doing explainable explainable machine learning recently. And so her talk basically started to break the term explainable apart. So rather than having a neural network that we look at what weights it uses or what are the inputs that are important, to actually have a system that is deterministically explainable. It's not explained post hoc. It's a part of the reasoning, like a decision tree. You can actually interpret it totally. So that's what drew me into this paper. Now, how do I go this? There's my mouse. Okay, and then if I move that here, a bit better. So what they do is they doing wrong here. Okay, so sideways. They say that they get good results. They say that they can do reasoning on these networks. They start by what do? They start by defining concept neurons and differentiate, and they build these up into multiple layers. The beauty of it was that the subconcepts can be learned. They don't need to be defined in the data set. The concepts are in the data set, and they're essentially the labels that you have that you're trying to learn. It will break down into subconcepts and hopefully find these subconcepts itself. They have different types of layers in the network. Input layers. Where are we there? Input layers, differentiate layers, subconcept layers, concept layers, convolutional filters, and deliberative neurons, and there are more here as well. So I like their initial diagram here, that they say that really what you're trying to do is, in this data set, separate fruit versus vegetable basically on what fruit it is and whether it is smooth, what its length is, what its color is. That gives you the concept of an apple, which it doesn't know at this stage, but then it will, essentially learn those input subconcepts and the fact that it's an apple, and then put that into the fruit basket, and then we can examine it afterwards and sort of interpret which subconcepts we've got. I would have preferred that they did this example in the MNIST dataset, one of the datasets they've actually used, because it's not clear from this diagram for me as to which of the inputs and outputs and which layers feed into which. Okay, what can we do? Go here. What did I want to say? Okay, so if we go back to the in the situation of the MNIST dataset, the first one that they talk about, they have their input layers. They then have these convolutional filters. They have a differentiator layer, which remember that is D as opposed to A. So each concept pair in turn is differentiated from each other. So we have a layer of differentiator layers. Then we have some concepts, which are, these are learned. And then we have concept layers, and then we're out. And okay. Looking through the code, I don't know if I should turn this into. sorry, I'm mullering this a little bit. Classification problems. Okay, as I said in the preamble, I managed to get the code down. The code is available in DigitalOcean, and it runs quite with very little effort to get it to run. It took me 2.5 hours on a CPU machine to get it to run for the MNIST data set, but that's fine. It's apples and oranges. I did notice here that the different times depend on the type of problem that it was trying to solve. If we have a perception task, then the training time is longer for the ENN. If it is a symbolic reasoning task, then the ENN time training is far less. I didn't dive into the max sat problem set. Has anyone looked at that before? Does anyone know what that is?
So I don't really know what it is. I looked at it very cursory, but basically what I think the problem is that you're trying to solve is you have a set of logical clauses, and you want to see what's the maximum number of them from the set that you can combine, and they'll still all be true. So you could combine 2 and they would both be true, but you might be able to combine 3 and they might both be true. And figuring out what's the maximum number is a NP hard problem.
Okay.
And so that's what they are trying to get the network to do.
Yeah. Okay. Got it. And so it's combinatorially expensive.
Mm-hmm.
Yeah. Okay. Then. Okay, so what you take your network, you train it, and then what you can do is it starts giving you these subconcepts and concepts. On the MNIST dataset, they then start looking at a failure case. Jump in here now. Yeah. Okay. No, I'm going to jump in the other way. So when you start training the network, you start seeing this is a comparison of gradient descent networks and explainable neural networks, and they start looking at the weights in the neurons and how much they're firing. And here we start seeing in layer 1 neurons versus layer 2, and again layer 1 versus layer 2, you start seeing that the differentia neurons are far more, they're focusing their attention, and the concept is focused in a fewer number of nodes compared to, say, a traditional neural network. And then when you start
wondering what these diagrams meant, I couldn't understand it. That makes sense.
Okay, good. And then by the time you start getting through to the subconcept neurons, this cleans up massively. So there is almost no loss, no faulty activation in the neurons here, whereas there are in the gradient descent neural network. So this is one of their arguments, saying that this is it's cleaner, it's more interpretable. You don't have to say that the network is, it might be looking here, and this might be a positive weight, and this might be a negative weight, and I've got to interpret it. You get far more deterministic and explainable reasons. So if you're looking from 1 and a 9 here, you can see the different weights, what's positive and what's negative, and that actually starts to look like the figures. So I liked that. They then start looking at a failure case. So this top figure here. Scroll. I hope that can people see that okay. Scroll it down. So failure case. So this is the input images of 1. It was classified as a 2. Now we can write a 2. We can write a 1 with a hat on the top and a crossbar like this, or we can write it just simply. And of course, this 1 is starting to almost reach the zone where we would, as a human, have problems recognizing it. If this top corner was curved a little bit more, then I'd be pretty certain that I'd say it was a 2. So I liked this explanation, and the interpretability of it, but it also started to make me think that we may be able to get away with far more exemplary images rather than examples, rather than a large training set. Seeing this might say that we actually need some more, ones or examples in the data set. And then we could more easily, compared to normal neural networks, test the usefulness of them. They then proceeded to delete neurons from they wanted to see how robust the network was. So they started to delete neurons from the network and see how badly the training error went. And what they found with the gradient descent neural network, that different classes sort of fell out at different times. Whereas the ENN, one class fell out at in turn, suggesting that that there is less redundancy in the network and that it's smaller.
Did they choose the neurons that they take out randomly, or did they start from top to bottom, right? Because
they say it was random, but this looks very, I don't know which colors mean what. So yeah. I don't know what that is. Yes, so I agree. That's an open question. I tried to understand this this chart here, and I couldn't understand this one. So I don't know what this means.
Me neither.
Okay, so now I'm going to get into some of the sub-concepts.
Wait, actually, I think I'm seeing it now. It's the number of, saying the number of sub-concept neurons versus the test error, but I don't understand the dots anyway.
Yeah, and I haven't found the code to reproduce this yet, so maybe I'll find it, maybe I won't. Yeah. So what they tend to do is they start to talk about how do you find the sub-concepts, because essentially what the network is doing, is my understanding of it at a very high level, is it breaks the input space down to a number of sub-concepts that are learned, and then we're applying almost Boolean logic on those to come up with the concepts that we want the labeling. But these sub-concepts need to be learned. How do you do this? So what they do is they start clustering the input space. The code looks like it splits the input space into a linear zone for each label. So in MNIST 0 through 9, we take all the data that is a 0. We then take the input space. We sort of start split into some kind of linear space, or not. I'm not sure exactly these steps, but they break it into 60 concepts. And they find 60 clusters. Then they step up through those clusters. They find a hierarchical tree of those clusters, and how, as you change the number, they combine into one another until you've just got, again, one cluster that contains all your data. They then cut that at a certain level to keep a standard number of clusters for each digit or each label we've got. So you may end up with 10 clusters for 1, 10 clusters for 2, 10 clusters for 3. And then it is those clusters that then essentially become the sub-concepts that are then you then train your differentiator and concept neurons on, as I understand it.
So I looked into that part of it, because I think that the idea of sub-concepts is like a key contribution or insight of the method.
Yes.
And they use something called Ward's method.
Yes.
And based on my understanding of how that works, is it views every single data point as its own cluster.
Yes.
And then at each iteration, it will combine two clusters based on whichever combination has the least variance, like within the cluster, like the least increase in variance within the cluster.
Yes.
This is actually really interesting, because it also depends, I think, on what kind of distance you choose.
Yes.
So if I remember correctly, hierarchical clustering can look very different if you choose slightly different distance measures. And so there's this quite a important degree of freedom there for the person who is training the model to decide what sub concepts can be learned, I think.
Yeah, and for Ward's method, you have to use a Euclidean distance, but for other methods, if they used another hierarchical clustering method, for sure they could use.
For example, when they say at the very beginning, right, they have the vegetable example, the input space would not be a pixel space from what I gather, right? So there it becomes a lot more difficult to talk about what is the distance in that space, distance between colors, for example. Also, so
yeah,
makes it yeah, slightly ambiguous.
Mm.
Yeah, I think you're combining dimensionality too, like distance in color and distance in size and distance in shape. Like, what do I mean?
Yeah,
absolutely. So, and then I liked this, and then I think I felt I understood that much of it. Then they start talking about the rectangle data set. And so this is where they synthesize many rectangles that are either horizontally oriented or vertically oriented. And they ask if it can generate. So can we, unseen rectangles, can tell me whether it's a horizontally oriented rectangle or vertically. And that seemed quite simple to me and quite nice. And then but what really struck me was this, the loss function here. No, this wasn't the, so this was the, okay, sorry, they've gone to the Boolean logic gates. Okay, so okay, they're on, apologies. So then they started training a pair of Boolean functions on all 16 variants that they can do. And then they managed to condense the output of the system down to a logic gate and logic flow system. So what they did is they actually used the A and B as one true, false, the binary. All the data to the system is binary. You can only do binary data. And then they passed in which function they were using, and they did that in terms of one-hot encoding. So, so then you've got, again, another 16 bits that you passed in. And then the logic came out if f is, if the index of x is smaller than 6, then and they came up with this circuit that could do all. If you pass in a, b, and f, it will give you the correct value for all 16 pairwise Boolean operations. And so the system learned this, they say. And then what I really liked was the cleanness of the decision boundaries in the decision space, which makes sense. You've got binary input, you're learning what is close to me, what is far away from me, and keeping it pretty much in a binary state. They also go on and ask about, and say that what was this one again? This was the D, this was the distribution difference between the decision boundaries. So here they're saying that the decision boundaries between two, sorry, this is back to EMIST. The decision boundaries were further apart in the EMIST handwritten digit state, which I think this is 0.2 of a pixel. So I'm not sure how significant that is, but yeah, this graph here I totally again did not understand. They say as the noise level reached 1, that they had a test accuracy of 60% and GDN had a test accuracy of 35. So I don't quite understand how that's measured.
Maybe it's trying to measure like out of distribution generalization. So like the more noise you add, the less similar the digits are going to look from the training set. So it's trying to show that that the what is it? It's essence neural network, the ENN, generalizes better, something along those lines. Or maybe it's just that it's more robust to noise.
And I suppose if you're adding 100% noise, that means that every pixel is perturbed by some amount, but yet some of them it's positive, some of them it's negative.
Would that maybe be the noise level relative to the signal? So basically would say that half of the pixels might be flipped?
Yes, yes. If it's signal to noise level, then yeah, then I can understand that you could still get 60, 70% on it.
Yeah.
That makes sense. Okay, that was good. That's good. That's good. Okay, and then for me, the final bit really for me is the supplementary text. That's the code here. So for the main train ENN, it's 1,300 lines. Large amounts of it just reading parameters in and out. The parameters, it's nicely encapsulated in that you just pass a one and then it uses some parameter set quite nicely, which I thought was, good on them. Did anyone else look at the supplementary tables?
I haven't had a chance to look at them.
And so here what I found was very nice, or that blew me away a little bit, was the traveling salesman problem. That and a few of the others, what they started, so the orientation problem, they started turning the outputs of their explainable neural networks into pseudocode. So here's the pseudocode that they've got. And so I think that's really powerful. I think the circuit diagram that they had for the Boolean operators was the beginning of this, and that any way to sort of automatically do this would then allow us to check errors and failure cases far more robustly. So I was really impressed they did this, and they actually compare these back to the state-of-the-art algorithms, and they say there is some commonality between them, which is nice.
Sorry.
Yeah.
One question I had about this is how similar are those last couple layers from the differential layer to the concept layer? They seem very similar in logic to a decision tree.
Yeah.
And so I was thinking that in a way that it seems like they are encoding a decision tree at the end of the network.
Yeah. And like it's sort of the yellow and the thing. Yeah. I mean, they do pass depending on the task, they change the sigmoid activation function. They do change that for a square activation function.
Yeah, for the logic tasks.
For the logic tasks, they do that. And yeah, it does seem to me very much to be, and especially because they have a part of the algorithm prunes nodes out that aren't useful for subconcepts. So they dramatically, aggressively try and kill nodes. So that will mean that it will very much come down to be a kind of a more like a logic tree. They also say that if they start training with gradient descent, then they get a small percentage increase, but very little, which I found interesting. And the one that blew me away the most, and I don't know if everyone else has seen this, is that I'm not sure which task it was now, I forget, but they took a trained ENN and they took the weights for that as for a GDN, and then they continued to train the GDN, and it found the same solution. Great, you'd expect it to do so. Now they started to perturb the initial weights of the seed weights that they had, and they found that you only need to get to be about 1 to 3% perturbation, and then the GDN would no longer learn. Go off to another solution that wasn't as good. So to me, I found that very interesting, because it said to me that the regularization of gradient descent smooths the loss function so that it can't find this in the loss function, this crevice or whatever that the ENN has found, and so can't find such a good solution at that point. It's got a smoother loss function, and so it'll find the global minimum on that surface, which may or may not be as low as what this one can find. The problem is if you allow your network, if you don't regularize your network, then you can very much, for gradient descent, you can very much end up in a local minimum, in a crevasse that's not useful. So yeah, I quite like that.
Yeah, that's interesting. I think it does, all of this points to the fact, a lot of this points to the fact that gradient descent without inductive bias as a method can like converge on a very poor local minima.
Yeah.
Yeah. I also really like the fact that you can generate pseudocode from these methods. I thought that was really cool.
Oh, that's really impressive, because then you can go into, like, if you've got a, I don't know, self-driving car or a nuclear power station, you can go to the effort of doing that, and you can go, okay, what are the failure cases that it hasn't found? So, which I really like. I don't know if I'll get the time to try and generate pseudocode automatically, but part of me would like to try and do that.
Yeah, that would be cool.
Sorry, I haven't really been watching time. I've just been flying through it. I took it at a higher level, so I'm not sure if people want me to drop into more level, or if a level of detail, or if there are more questions.
I would have one question. So right now we have these differentiator neurons, which for each concept compare against all the other concepts, right? Yes. So would we expect that this scales quite badly, right? So if we have 100 concepts, suddenly we need, what, 10,000 of these neurons? And in real life, if we look at any picture, we have gazillions of concepts we would assign with any car, house, and so on and so forth. Would that be essentially, yeah? Do you think it would be possible to get to the point where it gets human-like abstraction levels just by scaling it upward, or would it hit a boundary there?
That's a really good question. It is using support vector machines heavily, very, very, very heavily, and I can't remember the upper bound on support vector machines. So I presume they top out at several thousand dimensions, would be my feeling, and that would depend on, you can change your kernel and you can get some funky separations based on your kernels, but I think there'd be a limit there. So then what we'd have to do is I'd have to do a hierarchy. So, well, this is what I'd be tempted to do. So is this an animal, plant, mineral? Then is it a whatever? And then is it a, and so deal with it that way.
Was the support vector machine actually crucial here?
Yes.
Or would, because the way I understood it, it was the crucial step was the clustering, because the clustering is the thing that actually gives the concepts or subconcepts, and then any method that you can find that essentially maps it into a binary form should be good. Support vector machine might be good because it's fairly robust, right? Because you have a level of how you want your decision boundaries to be wide or narrow, but in principle, I would have thought that any classifier of some sort would be roughly similar in strength.
Yeah, maybe.
Because the way I see it, it's essentially feature engineering plus model stacking that seems to be good, and that is known for a long time, that this has a quite beneficial effect on model performance, right?
Yeah.
They do say in the discussion that one of the extensions to the work is to use other binary classifiers besides an SVM. Like even one of them is a perceptron.
Yeah.
So yeah, I think that maybe the method is agnostic to the type of binary classifier you use. Not sure. We would only know through future work. One thing that I think is, so I was thinking to myself that this method is really interesting in terms of results, and also just pointing out a lot of the benefits of this type of approach. Another one, but as Arvid kind of pointed out, that it's not these concepts have been thought of before. And I think one question is like, why aren't they used in state-of-the-art performing stuff and performing networks? And one opinion or hypothesis I have is if you look at the results in table 1, the method performs relatively poorly on CFAR 10. So CFAR 10, in my opinion, like the input space is a lot more complicated than any of the other problems that you look at. And it's harder to come up with, as easily to come up with sub-concepts which help to differentiate, especially in an unsupervised manner.
Yeah.
So based on the discussion that we've just had, I would say two things I think are, one, this method probably doesn't, like using an unsupervised method to find the sub-concepts, especially like hierarchical clustering, probably doesn't scale well to large input spaces or complicated input spaces. And also, it probably doesn't allow you to find concepts for complicated input spaces, sub-concepts for complicated input spaces, like a sparse enough, a small enough number of them that can still help you differentiate. Like, so you have to create like 100 by 100 sub-concepts and 10,000 differential models.
Yeah.
So I think there's something there, but that's just my idea.
And I agree with you there. And then I think that then if you're going to try and push something like this out into production, it would be, do you at that stage just need to show a single prototypical example of each subconcept, if you happen to know what subconcepts are, and you can lead the system by doing that? Or do you actually, and is that enough? And is that useful in your actual situation? But I think you're right, you'd hit a limit on the number of concepts that you can do computationally wise. And it's not practical to do that. Yeah.
What's really actually fascinating is that the choice of having a decentralized network or a localized network seems to be, at least performance-wise, not that drastically different, right? It's I think that was what flabbergasted people at the very beginning, that you can have a huge network that apparently, the neurons, each neuron has like multiple functionalities, and here they show that it doesn't have to be like this. You can actually have it localized in the sense that each neuron, as you said, you know what it is, and it seems to be replicating how our brain apparently seems to be working, right? If we potentially could silence particular parts of our brain and therefore would eradicate certain concepts in our understanding, which is cool. I think really, really cool.
I think it is. I mean, I'm just itching to get the time to pull this apart more and try it on other real world examples.
I was thinking that the method itself, I know they use a non-gradient based method, but with like a code base, if you use PyTorch, you could implement this whole thing, train it using gradient descent. Like even the hierarchical clustering part of it could be incorporated as like kind of like in an expectation maximization like algorithm into training into the method. So I was thinking even that could be really interesting, because I think that the main idea that's interesting is the hierarchical clustering beforehand to determine the architecture of the network, and that using gradient descent versus using another optimization method isn't as important. Because so I would be interested to see if they do that, what it would be like. One thing that
So what also would be maybe quite interesting is these clustering methods that might not be hierarchical, but where the number of cluster is adapting parameter. There are these Bayesian variants, and I never worked with them, but that could be also quite cool, because right now I think that there seems to be quite a strong prior influence on choosing how many clusters you ultimately end up with, how many sub concepts. But if that would be something that would auto-tune itself, that might be quite powerful.
Can you repeat part of that again? Because I think there's a pruning part on the subconcepts and concepts. So can you repeat that again, please?
Oh, sorry. I was thinking that there are clustering methods that use Bayesian Bayesian methodology, where the number of cluster itself is a variable that gets optimized alongside the number of clusters. And this could be perhaps quite powerful in such a setting where, I mean, I'm pretty sure there's still some hyperparameter on what the expected number of concepts probably would be, but you wouldn't choose the exact number. So that might be something that one could incorporate into this as well. I think there's a lot of power in this unsupervised learning that makes this work so wonderful.
And also, you could use the number of subconcepts that it's come up with. You could use that as a sanity check as well. Like, yeah. would I expect 1 million subconcepts in handwritten digit recognition, or would I expect 5?
Yeah.
And can I interpret some of them, to make sense?
Perhaps a little bit like last week's paper, where they had the more difficult to differentiate pictures, right? Of some, I think it was a seagull or what I read there, and I would almost think that this is the number of concepts you choose, right? So the more concepts you choose, the more of a specialized expert you get, but yep. Perhaps you have a harder time seeing the broader picture. I don't know.
Absolutely. And then the number of concepts that you pay attention to.
Yeah, precisely.
So here, okay. Peter?
Oh, go ahead.
Okay, I was going to tear off into a totally different random subject. There was an article recently so that they were showing that the expected stimulation, the accepted reward based on the stimuli in reinforcement learning, well, actually, this is actually in bees, physically in bees, that if you learn, something like, I know the last week's paper, that this has got a blue foot, so therefore it's this type of bird. If you learn the wrong concept, it is very hard to unlearn it. Was the downside, the result of the paper, and so, and I think it's very much this as well. If you find the wrong subconcepts and you build layers and layers on them, certainly in biological systems, it's very hard to unwind the wrong concept, even if there is better data there.
There was a biological paper, or was it a computer science?
It was on the boundary between both. It was in Nature, and they used bees. I can send the link to you if you want. They used bees. They put them in little things. They actually tracked. They could, through light, they could actually track the individual firing of the individual neurons.
Yeah. And
they gave them sugar. They gave them a stimuli, and then they gave them sugar. And based on the stimuli, they learned that, this is the amount of sugar that I'm going to get. And then when they surprised them down or up on the amount of sugar or the sweetness of it, they found that there was sort of a correction firing going on in the neuron in the bee's brain, which I thought was really nice. And they were using it for inspiration into neural networks and how to correct error in reinforcement learning.
Mm-hmm. Oh. Yeah, if you can send that paper around, that would be great.
Okay, will do.
Yeah. One thing I do like about this paper is trying to find a novel inspiration for like a machine learning algorithm or a machine learning algorithm or an AI algorithm, because I do feel like there's a bit of an echo chamber in terms of like, I mean, it makes sense. You're constantly trying to develop upon the research that's happened beforehand, but in machine learning, you see a lot of the same type of math being used for things.
Yes.
And not a lot of like really crazy ideas being
used.
But that's also probably because the crazy ideas mainly don't work. But it is nice to see a paper where you have some more some ideas coming from another field, which help introduce some like new ideas into the field. So that's a cool part of this.
I agree, and I'll take that a little bit further and compare it to last week's paper as well. I'd say that there is a there's a tendency to a microscopic feature, like a small feature that improves something. And it's very hard to step back to the broader level. And I think what this paper is combining a few topics and known techniques from other from other fields, and then getting a good result. And the magic, I'm always sad at this paper because the amount of the magic of the black box is just being held into a small area, which I kind of want magic to be there, but from a usability point of view, actually, I don't. I want it to be interpretable.
Yeah, I agree with that. I actually, and one thing about this paper is like those, I view like the differential layer and then the subconcepts layers and the concept layer, those could just be like the last three layers of any classification network. And I don't see why, as an inductive bias, that maybe that's a really good inductive bias. Maybe the only hard part is that you have to do this hierarchical clustering beforehand, but it could be interesting if this, that's why I was asking, like maybe follow-up work leads to finding a way to create like much better classification networks just by using this inductive bias at the end of the network and finding maybe a better, a hierarchical clustering method that is better for these more complex input spaces.
Then maybe you could take the hierarchical clustering, run it from the other end, run it top down rather than bottom up, in that you start looking at your data, you've got your labels, and then you go, okay, now I need to find some concept that splits these two. That's not enough on a binary split, so now I need another concept, and then start comparing and contrasting those. And that's the actual learning process, is finding the, might be intractable.
You can always find a greedy solution, which is like very tractable though. So, and that's one of the things that they pointed out, is that the network, like for the traveling salesman problem, it found a greedy algorithm to solve the problem, which isn't optimal, but it is one way of solving it with a good enough solution. It's just like, I remember, I don't think this is always true, but you can use like k-means clustering to come up with the parameters of a Gaussian mixture model for some input space. And if you compare those, and that's usually what they do when they, as the way to initialize the means and variances of the Gaussian mixture model.
Yeah.
And then you use expectation maximization to find the optimal parameters, but they're not that different often. Like they're very similar. So you could use like this method that takes almost no time, and then you have to use this method that takes a lot of time. And so, yeah, there might be a quick and easy solution to it.
Absolutely. Any more thoughts or questions or comments?
Okay, well, then we can finish a little bit early. And this was a really cool paper, Dwane. So thanks for presenting it. Some new interesting ideas coming out of there instead of the same conferences, although I do enjoy those papers too.
Thank you very much. It was a very good choice, I think.
Yeah.
Okay, great. Thanks, guys.